And now live from Mo's professional studio, someplace in Austin, Texas. This is Howdy Partner.
All right.
Take it away, Mo.
Thank you, Ghost Host. Tried to do my best McConaughey impression there, but it was awful. Welcome to Howdy Partner. I'm so glad to be back. It feels like it's been ages since the last time I was a part of this, like an episode. So super glad to be here. With me are three incredible people, one of which I think you all know already, Hanara. Do you want to introduce yourself?
Hi guys, I'm Hanara. I'm a partner solutions architect at AWS.
Right, resident genius. Don't let her play herself down. And then today we're joined by Flowmill and two incredible guests at Flowmill. Jonathan, do you want to introduce yourself first?
Well, hi, I'm Jonathan. I'm founder and CEO of Flowmill. Yes.
All right, and then Mike.
Yeah, cool. Hi, I'm Mike Cohen. I am, COO, co-founder at Flowmill.
Cool. So we have a lot of stuff to get through today. Super exciting stuff. But for everyone who hasn't watched an episode of Howdy Partner before, Hanara, can you fill everyone in? What is this show? What do we do here?
So Howdy Partner is an AWS Twitch show where we invite over some of our AWS partners and just chat about their solutions. So we get to go through some demos sometimes and get to know a partner's solutions a little bit better on a more personal level that's a bit more casual here on Twitch.
Nice. And who should watch this show?
Anyone who's interested in getting more acquainted with the cloud, yeah, I think it's totally free for anyone who is interested.
Right. So developers, architects, anyone who's looking to learn more about AWS and our AWS partners, feel free to follow along, participate in the chat. We're super excited today. We have some awesome demos from Flowmill. But first, I wanted Hanara to maybe set the stage about what we're talking about today. I think it's network observability. What does that mean? What is that?
Yeah, so I'm going to do a brief overview on observability in the cloud in general, and then we can take it over to Flowmill on the network observability. So observability on a very static definition introduction is just a defined way to measure how well your internal states of the system can be inferred and analyzed with its external outputs. So that probably just doesn't even mean anything, that just sounds way too technical. So basically, if your internal system is supposed to tell something more meaningful to your developers, it should be doing that if it's working correctly. So a couple of benefits that you can get from observability into your AWS or cloud infrastructure is that it helps you a little bit more than just monitoring, as it allows more defined and intricate details of what's going on in your system and can help discover unknown problems that you might not be able to see just from a very surface and superficial metrics that you'll see. Like with CPU, you can probably have a very good CPU level, but that doesn't really tell you anything about what is happening with your application. It's tough to catch memory leaks. Sometimes your application can work perfectly, but sometimes it crashes randomly. Or even if a customer is submitting edge cases that maybe you haven't really thought about, your application might still work, but not as good. And you can kind of infer, but you're not really getting the kinds of information that will help you action on items and have the confidence that your highly distributed application is working the way that you want it to. Personally, observability has saved a lot of time and grief for me when I'm developing on the cloud. Just pinging your endpoints is not going to help you resolve your issue. Maybe you can in 5 hours. Which I've definitely been a victim of, but having that kind of ingrained visibility into your cloud infrastructure can definitely help you resolve those issues, and have multiple roles also be able to diagnose issues in your AWS cloud infrastructure, because not everyone is going to be such an expert in every single part of a full stack website. Like, I'm one person. I don't know all the ins and outs of networks. I don't know all the ins and outs of developing and the perfect algorithm. And if I have something and the tools that allow me to look under the hood without knowing every single part, it allows more people to understand what is going on in the application, and you don't have to have one expert to just kind of ping on a very superficial level to get a basic inference. But yeah, so observability is super important to maintaining the health of your application and just having that confidence that everything is working the way that it should be. But yeah, that's a quick overview of observability. I'm going to hand it over to our Flowmill folks.
Hey, thank you, Hanara. So Jonathan here. Hi, everybody. I want to give you a little bit more of in-depth background, like the 45-second version of it. I've been building observability solutions since the mid-2000s, as I was serving in intelligence, and we built our own observability solutions and then automatic and semi-automatic mitigation based on that data. You could see how it changed people's lives. Kind of people would sleep better, not get paged in the middle of the night, and our systems got significantly better. I moved to MIT in 2010 and did a PhD in monitoring systems. How do you create systems that can process massive amounts of telemetry with very low overhead and low latency? And we focused on network observability and decision-making for network. Throughout these projects, we had collaboration with Facebook. I'm a Facebook fellow, and we deployed many of these network scheduling systems in production at Facebook. So we were able to, for example, this one system called FastPass, we were able to scale it to 2 terabits a second of scheduling with 50 microseconds of latency. So very big clusters with very low latency of scheduling. And so at Facebook is where I got acquainted with eBPF, which I'm going to tell you a little bit about, and how do you get observability with eBPF. And that's how Flowmill started. So
eBPF,
what I'd like to,
right?
eBPF, Extended Berkeley Packet Filters. I have a slide on it in 3 minutes or so. Okay, so what I want to talk about today is what about flow monitoring? How do you monitor how your different services interact on your cloud? And how do you do that with eBPF? So for the introduction, I want to cover why do it. So how do you get visibility into your architecture, into the health of your services, and the cost that you're paying for running your deployment? I'll go through an example of how you can gather this type of data on the command line with Kubernetes on Linux. Talk about the pros and cons of doing this versus other ways of observability, and then talk about the problems with command line tools and why you would really want to use eBPF. I will then hand over to Mike, who will show a more extensive demo of what you can actually do with this data and kind of interact with it more. So I'm going to start with just flashing a few screens to motivate, and then Mike will give a more extensive demo. I'm really looking forward to this. So
cool.
Let's start.
Like I said, Jonathan and Mike are the experts, right? I mean, you heard intelligence experience, MIT, Facebook, you running the gamut here. So yeah, pay attention closely. I'm sure everyone's going to learn a lot. I certainly did when I got a preview of what we're doing today. So yeah, jump on in, Jonathan.
And I didn't even introduce Mike, and we have a team, kind of a team of stellar. So, okay, great. So let me start by introducing I'll share my screen. Introducing the demo application we're going to work with today. It is an open source project called Microservices Demo. It is on GitHub. You can see it. I'd like to thank the developers because this has been one of the workloads you can really demo with and show a system with microservices running on Kubernetes. You can show it very effectively. So thank you to the developers. It has a handful of these microservices written in multiple different languages. So you have Go, C#, Node.js, Python, and Java, all in one microservice deployment. So this is what we're going to see today. We have deployed the microservice demo on EKS. So here you can see our load balancer. It is an online shopping experience, a demo online shopping experience where you have multiple products. You can click through the product catalog. There's a shopping cart where you can add products to your shopping cart. And finally, you can place an order, and it has a handful of services to handle orders. So here, went through kind of a workflow with the microservices demo. And with these types of services, you'd want to see kind of how the system is built. Let me move to my command line here. Let's look at this Kubernetes deployment. So I'm going to use kube control and get the deployments, what's running here.
No, you call it kube control? That's always a debate in the chat, right? Kube cuddle, kube control.
Oops. Let me get my token again. Can you see this? Probably not. Okay. So let's get our deployments. Yep. So here you can see the different services. You can see there's a front-end service. Here's the load generator that's running. Cart service for holding the shopping carts. So there are even ads, which we didn't see. It's what you would expect from a multi-service shopping cart. Usually you would have kind of in a real deployment, you'd have maybe tens of services, not tens or maybe kind of hundreds of services. Here you can see the pods. There's like a handful of replicas serving some of the more critical services. And so usually what you get are these views of the system from the configuration side. Right here are the services. So you can see the system in different kind of projections. The problem is, we get to see kind of these pods, but how is the system built? How does it interact? This is critical when you want to operate it. So usually, when you look at one of these systems, you want to see kind of a diagram of how the system is built. And microservices demo comes with one of these diagrams. You can see it right here. So what are the different components that are connected? So the first problem kind of many operators have is they have a deployment, and it's frequently a lot more elaborate than what is shown in this diagram. And how do you know what is connected to what? What is the state of my system today? Not when somebody updated this diagram, but right now. So these types of diagrams are notoriously out of date. What you would want to see is a live view of your deployment. What is happening right now? What components are connected to what other components today? What are the external dependencies? Right? Is there a service that depends on an external dependency? What is the status of these external dependencies? Right? Like which parts are connected to the internet and so on. And here, I'm not going to go into more detail than that. I'll let you'll see a more in-depth demo soon. Once you've looked at the architecture, you want to understand how your system is behaving. So let me jump here. Maybe here is the number of HTTP successes, right? Like what happened in my system? How did it evolve over time? You want to gather that across all of your services to understand what is happening. And then when there is a problem, how do you figure out kind of what's happening? Like in this case, we have a reduction in HTTP 200s. Is it because HTTP 500s increased in this case? No, right? Like, so how can you find out what happened? Did we get a lot of 400s? Did we have an increase in latency and so on? So how do you get a lead into understanding what your kind of how your system is behaving? And what we found, I told you a little bit about network monitoring. We found that monitoring the infrastructure and how your network is behaving is very hard with today's tooling. So you have application layer monitoring, but you don't see kind of the underlying infrastructure. So is the network performing like it should? Do you have our round trip time staying for your system? Do you have a lot of packet loss and retransmissions? Do you have a lot of connection failures where systems are not connecting? Do you have a lot of new sockets being established, bringing your system down? Kind of like, are you DDoSing yourself and so on? So how do you see to get health information from the infrastructure? And finally, cost. Let me collapse this. Finally, cost and network-related cost. So there is a cost both to AWS and the tenants running on AWS, kind of the cloud users, kind of you as you deploy your system. There is cost for sending traffic between availability zones and out to the internet. So how do you know which service is sending traffic both across zones or to the internet? And when you figure out which service is sending that traffic, how do you know what is it sending it to? So how do you know which edge, which interaction you need to optimize so that you can control your cost? This is data that is really hard to get.
I have a question. Is this able to trace through Lambda?
That's a great question. We'll talk a little bit more about pros and cons in tracing, because the short answer is this does not do tracing. Kind of this system monitors each service that you have and all the connectivity between pairs of services. So it doesn't trace through a Lambda, but it would see connectivity to a Lambda.
Gotcha. Thanks for that.
So I hope to cover more of that in a moment. Great. So let's move on. Let's go back here. So we've talked about these three major benefits: architecture, health, and cost. Let's go through how you can assemble this type of data from a system. So how do you gather this flow data? So from the sockets, you can gather at different points of time who is sending to whom, both the IP addresses and the port numbers. Right, IP addresses, port numbers, and then you can gather statistics about how many bytes were sent, how many drops. You saw these statistics on some of these dashboards. What is the round trip time? What is the error code? So you can count these together. From your orchestrator, let's say it's Kubernetes, but it could be Docker or ECS or Nomad and other orchestrators. You can gather for each one of the pods or containers the IP address for that container and metadata for that container. For example, the name of the pod, what container image it's serving and what tag of the image, where it's running, in which availability zone, and so on. By marrying these two data sets, one from the operating system and one from your orchestrator, you can get a coherent view of how your system is behaving, how a service, a specific container running in a specific availability zone on a specific host is talking to another container in another availability zone on another host, together with the telemetry on, what are the failures, what is the health of the system, what is the performance of the system. So let's go through some pros and cons. Why would you want to do this versus other techniques? So with flow monitoring, what you could get is instrumentation with no code changes. So I've shown you how you extract information from the operating system, from Linux, and from your orchestrator, for example, Kubernetes. Here, you don't have to change the applications. You don't even have to change the configuration of the applications. You don't have to change any YAMLs or Helm charts in order to get visibility. You get 100% coverage. Unless you're using some very specific technologies, all of the communication between your containers flows through the operating systems, through sockets. And so kind of if you're using sockets, which is overwhelmingly most users do, you get 100% coverage. Everything goes through the operating system. You can collect this information with extremely low overhead because you're instrumenting a very high performance system, which is the operating system, and you can hyper optimize your collection infrastructure in order so that the collection would not cost a lot of CPU cycles. This is completely passive, so it doesn't add any latency to your code, to the running processes. So you can have a very low overhead system. And you can see not only the systems that you're running your collector on, but also externally. So anything that you have a collector running on that operating system and it talks to external APIs if you're using a payment processor or so kind of some other external API, external databases that are run by Amazon that you don't run your machines on. So you have AWS and RDS databases, you still get visibility into that traffic. Some of the problems that you can have with flow monitoring is when you have encrypted traffic, the operating system doesn't see inside the encrypted traffic. But this is solvable, even with eBPF. So you can have these probes that go into user space and instrument your OpenSSL and so on. I'm not going to cover this in this talk, but I frequently get questions. So kind of preemptively, TLS is a problem, but it's solvable. The other issue is custom metrics and distributed tracing. While you can use eBPF to collect data from custom metric sources or distributed tracing sources like OpenTelemetry, eBPF doesn't add the instrumentation. These collection technologies, right, like metrics and distributed tracing, require you to instrument your code. So eBPF would not replace you having to instrument your code with tracing, at least not the flavor of eBPF that I'm going to talk about today. So, for example, if you want to know the number of abandoned shopping cart, or the number of times you had to wait for some lock inside your code, this is not going to tell you. There are ways of getting this with eBPF, but not as part of this talk. With that, I want to go into an example of how Kubernetes sends data between pods and how you can use the command line in order to get visibility into what's happening between these pods. So in Kubernetes, let's say you have a pod A, and the pod A communicates to pod B through a service called X. The way Kubernetes implements services is by configuring IP tables with a virtual IP address. So X gets a virtual IP address. A talks to X. So I want kind of A resolves using DNS that kind of maybe the front end wants to talk to the shopping cart service. It asks DNS what is the address of the shopping cart service, and it gets an IP address, in this case an IP address for X. IP tables then translates this address X into an address B. So this traffic that kind of A thinks it's sending to X, what really is happening is that the kernel translates those addresses and translates A to X into A to B. And so that traffic goes out and reaches B. So B sees traffic as if A is talking to it directly. So let's see how you can extract from the command line information about these types of flows. So first,
before we do that, I just wanted to reintroduce the show. I see the follower count or the live viewer count is going up and down. So if you're just joining, this is Howdy Partner. We're here with Flowmill, and Jonathan is giving pretty good deep dive into flow data and network observability with their products. So Jonathan, go ahead. You were just about to talk about the CLI and getting flow data with the CLI.
Yeah, so in this example, you have a Kubernetes, a couple of Kubernetes pods. So pod A is talking to pod B through a service X. I talked a little bit about how IP tables translates the address X to an address B. So the traffic A to X actually looks like A to B. So at B, it looks like A to B traffic. So you see the orange annotations say what are the packets that are flowing between those entities. And so let's see what kind of command line tools you can run in order to get information about this traffic. So first, from the orchestrator, from Kubernetes, you can ask to describe the pod, in this case, A. So here you can see A has this IP address on our network. On the command line in Linux, you can ask the operating system to give you information about sockets. Here's the SS utility socket stats. And here you can see information about the socket. So traffic from A, and this is the same IP address as you see in the kube control run just above, A to X. And here you see there are some metrics like number of bytes. There are also packet drops, round trip time, and so on.
So Jonathan, is Flowmill mainly tracking and concerned with the observability on just mainly the network layer?
What Flowmill does is the Flowmill product assembles traffic from the network up and sees both the network traffic and how applications, how different services interact, and how the infrastructure and the network behaves for that communication. And then also analyzes the traffic, the payloads that are running on top. So you can see HTTP errors, for example. So it analyzes both the infrastructure and the application.
Okay, got it. Thank you.
Great. And I refer you to Mike's demo, which is just a couple minutes away. I've shown kind of two data sources, one from Kubernetes and one from the operating system, where you get information about a specific socket, a particular flow. And then you need to understand, I've shown you the purple translation that happens between IP addresses, because really communication is A to B and not A to X. X is a virtual IP address. So that you can get from the network address translation through the contract tool. So by stitching these three outputs from command line utilities, you can get information about traffic between A and B through X, and all the telemetry of number of bytes, round trip time, and so on. If you want to get deeper information about application layer, that I'll defer you to eBPF. I'll show that in a moment. Okay, so why not use command line utilities? What are the problems with those? So first, they have not ideal performance. What we've done here is we've run the socket stats utility that I talked about in the previous slide, ran it every few milliseconds to get information very frequently from the operating system. And what you can see is you pay millions of cycles for every run. And then for every live socket in the system, you have to pay a few, almost 100,000 cycles. It says 79,000 cycles in here. So if you have a highly loaded system, so you pay these 62 million cycles plus 79,000 cycles for every run, for every socket. So as you have more, as you have loaded production systems, this gets really expensive. You can burn a lot of CPU on running command line utilities. The other problem is that if you're going to use command line utilities, you are not going to get very good coverage. The reason is this. Usually when you run command line tools, you would run them let's say every second or every 100 milliseconds. So you have these intervals where the tool is running. What could happen is you can have events that occur between these polls. A socket could last 100 milliseconds. If you're polling every second, you're just not going to see a lot of the traffic that is flowing in the system. And even if you have long-lived traffic, you wouldn't see the edges just the start of the socket and the end of the socket. So this gives you very, very partial coverage. And this is where eBPF comes in. So let me tell you a little bit about eBPF and its history. The BPF system call in Linux has been around since kernel 3.18. That was, I think, September 2014. So it's been around for several years. And BPF has been since ported to several kernels as early as 3.10. So you probably have a system that supports BPF if you're running on a moderately modern kernel. What eBPF allows you to do is run some code on different events that happen in the kernel. So here, for example, when a new socket appears, when a new process appears, when a new container appears, when there's data flowing between on a socket. And it allows you to get information about what changed in your system. So instead of running a CLI tool where if you have 1,000 sockets open, you have to pay for all the sockets. If you have a system where only 10 sockets had some data flow on them, you only get information about what changed in your system, about those events that happened. eBPF also gives access into internal kernel data structures that you don't have in command line tools. So, for example, reading the content of DNS packets is something that you could do with packet tracing, but is not as easy if you want to write this type of high-performance system. You can get information about packet drops as it happens, more types of information about these different problems that can happen inside the operating system. UDP packet drops are very easy to gather this way. So those are the advantages. This is what kind of structural advantages the eBPF gives you. What is great about eBPF is that it has been built to be extremely safe. There is a mechanism inside the kernel that verifies the code and ensures that that code doesn't modify areas of the kernel that it shouldn't, and that it doesn't access invalid memory. So it is very safe. It runs in the kernel. You get information about the kernel, but it is quite safe in how code interacts with the kernel.
So we have a question. Sorry, Jonathan. We have a question from a techie thought. So does eBPF then run inside the kernel space?
Yes. So the eBPF is a specification of an intermediate representation language. You have code that you have in user space, and it compiles into this binary representation, and then you load it into the kernel, and then you can run it when the kernel is doing things like reading packets from the network card, or when a process starts, when the scheduler switches between processes, and so on. So yes, this code runs inside the kernel, but it is built to feel a lot more similar to user space programs that are safe, and it is very high performance.
Does Flowmill overall also run inside the kernel space too then?
That's a great question. So Flowmill has the Flowmill collectors have two components, and they have an eBPF collector so the eBPF code that runs inside the kernel is minimal, extracts a little bit of information about the kernel events, and then communicates that metadata into a user space application that then analyzes it, compresses it, encodes it, compresses it, encrypts it, and sends it to a SaaS backend for processing. So what it would feel to you is like a daemon set. So it's a container that runs on your system. It's a privileged container because it has to use the BPF system call. But it's a container that loads some BPF code using the system call, and then extracts telemetry that you can then benefit from.
Gotcha. Thanks for going deep with that.
Sure. So I talked about safety of eBPF. I just want to mention that it's extremely fast because the kernel takes this intermediate representation, and instead of trying to interpret it, it doesn't have an interpreter. The kernel compiles it into extremely efficient machine code that then runs. So you'd have performance that is like native code. It is native code after compilation. So it's great. It has great performance. So you get 100% coverage, no changes to the applications, and you have extremely low overhead and high performance in a safe system. So wins all around. I want to show you a little demo about to see how eBPF works and the type of data that you can get. Here I'm going to use this project IOVisor. IOVisor BCC. So BCC is the BPF compiler collection. It's an open source project that has several tools has some guides on how to write code, has some Python that interacts with BPF. And I recommend it as a starting point if you want to write your own BPF programs. So with that, let me move to, let me share my shell again. And I'll just move here. Here, I'm running inside a container with the BPF toolset on one of our Kubernetes nodes. Let me just clear the screen, and I'll run this tool called TCP top. TCP top uses BPF in order to monitor sockets, so it's very similar to the type of data that I showed on my slides a couple of minutes ago. So here you can see, let me pause this so we can go through it. Here you can see what process is sending data, what is the source and destination IP and port, and how much data is being sent. So you can see RX and TX. Here you can see the SSH where I'm connected to this node. So it shows everything on the machine, including this SSH running. Here you have the Flowmill collector running and sending some traffic to the backend and so on. Right here, cart service talking to probably the checkout service. So TCP top is a Python program, and you can go and read it. It has it has this C code that gets compiled and run in the kernel. So here, TCP send message, and has some Python code that then interacts with it and prints it to the screen. So let's see, print BP, sorry.
Oh, I'm having like traumatic flashbacks to my system class.
Well, the great thing about it is that you can build tools where you don't have to build the eBPF code, or a lot of the pain is getting the data out efficiently into a place where you can analyze it, and then making sense out of it, enriching the data with information from Kubernetes, enriching that data from both sides of the connection. So you get what process talk to what process, what container talk to what container. So that you can build tooling, and you don't really have to interact with eBPF yourself. You can package it into software like solutions, into things that have this code. Okay, so with this, I want to just go through how we had a question on what is in user space, what is in kernel space, how do you build a system like this? And I'd like to show our system architecture. So if you wanted to build a system like this, how would you build it? So what we talked about so far is the collector, right? The collector collects information from the operating system. So some of the things the Flowmill agent collects are information about containers, when containers appear and disappear, processes, and when they come and go, and what containers they're in, and when processes move between containers, sockets, network address translation. We talked about all of these. And then the Flowmill agent, the way you would build it too is probably you'd have these plugins that extract metadata from Kubernetes or whatever orchestrator you have. For us, for Flowmill, we built an AWS collector that gets information about IP addresses in your VPC. For example, the names of RDS instances, the name of ELBs, and so on. And also DNS, we have a DNS collector. That data goes into a SaaS backend. That this analysis pipeline that you'd want to run to analyze this data. And what that pipeline does is, in real time, it matches sockets from both sides of the connection, and enriches that flow information with information from orchestrators and the cloud and AWS, for example, and then creates these aggregates. Flow data is massive. There are usually even in a relatively quiet system, there is quite a big amount of sockets that are happening. So first, to analyze it efficiently, you'd have to encode data efficiently. You'd want to compress it, and then you'd want to have a system that efficiently analyzes it. And then create these aggregates where you can query your data without looking at all of the raw sockets. So how do you create kind of the Flowmill system creates these pre-computes a lot of the data that you'd see on the screen. This data goes into a time series database. We have been using modified Prometheus, but are working on kind of storage backends to make it more efficient. So you'd want to use time series. We use time series data for a lot of this data, and then you would the way we built it, and the way I think if you want to build a service like this, you'd build these APIs that work on top of the database to serve both a user interface or RESTful or gRPC clients. Just to make the system complete, there's also a statistic analyzer on top that you'd want to build, and alerting. You could use something like Prometheus's alert manager, but really you want to have kind of more, you'd want to be able to build logic that understands this type of data. And I think Mike, if Mike is going to show the overview page, you'll see some of that too. And so with that, I think I can hand over to Mike for a demo. But if people have questions, we'll take it.
Make sure to unmute myself. I think we answered all of the questions that I saw in chat. Obviously, if anyone has any other questions, please feel free to add them now, and we'll answer them as we can. But while we have some downtime, we might as well reintroduce the show. Today, this is Howdy Partner, first and foremost. This is a show where we talk about partner products and we dive deep on specific technical domains. Today, we're doing network observability, and we have Jonathan Perry, the CEO and founder of Flowmill, as well as Mike Cohen, the COO and founder of Flowmill. And Mike was about to take the reins and do a demo.
Yeah, cool. Thanks, Mo. Nothing more fun than live stream, live demo. What I was hoping to do today was show you how Flowmill works and do some, a little bit of chaos engineering. So Jonathan already showed you the application we're running. I'm just going to give you a little more background on the demo environment. So this is an EKS cluster that we're running. I have a small 3-node EKS cluster. The nodes are spread across 3 different availability zones, just to make things interesting. And as he showed you before, I know people may have joined. We're running this, little microservices application that has, these 12 or so microservices that represent an e-commerce sort of shopping cart application. So just to refresh people, this is what the, what the app looks like. I won't go through the trouble of showing you the app again, but this is the same URL Jonathan had showed you before. The first thing we're going to want to do, is get the Flowmill collectors actually running. So, as I mentioned, there's a SaaS backend that we operate, but you actually need to have Flowmill agents running in the cluster. They run as a daemon set, so we'll run root 1 across each of these nodes. Let me show you how you would actually get that going. So what we're looking at here, this is the Flowmill application. One of the first things you do when you interact with it is you would go to the agents page. The agents page has a little deployment tab, which can show you how to get up and running pretty quickly. In Kubernetes, this is super, super simple. The agents deploy via Helm. There's a kind of a pre-baked Helm chart that just gets everything going. And there's just a few commands. You would add our Helm repo, and then create a namespace for Flowmill and launch the Helm chart. Now, quickly, if you look, anyone will look at this line will notice there's a flowmill.yaml file which has configuration. You can get one of those by just clicking this button. That'll download it for you. I'm going to show you what it looks like in just a second, but since I already have it, I'm not going to download another one. But the flowmill.yaml, we can see here in my screen. Actually, it's just there's one configuration parameter that I change, which is essentially the cluster name. So you can call this anything I want. It's probably a good idea to call it like Howdy Partners. But really, this is just what it's a label that Flowmill will carry along all the way through. It does have a key that identifies where the agent will, how the agent can connect back to Flowmill and send data to the right place too. And then that's really all there is to it. Yeah, go ahead. What's the question?
I have a question for you from a techie thought again. Does Flowmill support AWS VPC network on EKS?
You can use AWS VPC networking, yes.
Cool. Would you have to change anything in the YAML configuration you just showed us?
No, because the level at which we're collecting data, you don't have to change. There's no knob to turn for it.
Cool.
So I'm not going to execute this command only because I've already done it right before we got going. But essentially, all I would do is paste this command in here, execute it, and it would get me off and running with my it would get me off and running and get the agents installed. I realize we're in the wrong directory. And then the way you would know once you got the agents running, you could do get pods -n Flowmill because they'd be deployed into the Flowmill namespace. And again, I can see here that I have my 3 kernel collectors. These are the daemon set that runs across the across each of the nodes. I also have my Kubernetes collector. So this includes actually a collector that will collect data from my EKS masters, and then also it actually talks to the AWS API. So there's an AWS collector that'll collect things like ELB information and other endpoints that Amazon knows about in the environment. So I'll show you how that works. But that's really all there is to it. Like, I don't do anything to any of these services or any of the pods. I didn't change any of the code. Since we're tracking all the sockets, we're able to map those back to figure out what service is doing what. So this is really all it takes to get going with Flowmill. Regardless of your cluster size. So
is there
once we have that,
for IPv6?
is it? Yeah, Jonathan, maybe you want to take that.
IPv6. Yeah, yes. It supports IPv6 with Kubernetes. You wouldn't see IPv6 as much. And I've just checked this point. It doesn't have any IPv6 communication that I could see. But yes, we support IPv6. The product does.
Okay, thanks for entertaining my interruption. Back to you, Mike.
No problem. No problem. Yeah, no, it's still more rare. I guess, V6 is still more rare in the Kubernetes environments. I don't even know. I forget what version, I'd have to admit, I don't know what version it would, support was added for it. But Jonathan mentioned, the layer we're collecting, we see all that anyway. So one of the places I'm going to start showing you guys is the Service Explorer. So the Service Explorer is our aggregated view of how things are communicating. So we take the socket data and we actually, aggregate that across services, which are running scattered across my nodes to show you what the overall system looks like. So since this is a small cluster, I can actually look at the whole thing. I can do searches and look at subsets as well. But one interesting place to start is just to look at kind of a subset of it. So as you can see here, we automatically built a map that looked a lot like what was on the GitHub page for this, for this application. You can see each of the microservices. You can see how they're communicating. If you click on any one of these edges or on any one of the nodes for that matter, you can actually get specific data on that service-to-service interaction. So you can see, in this case, this is HTTP. So I can see the 200 rate. There's no 500s at the moment. We'll work on adding some later. Latency, I can get network data like round trip time, packet loss, throughput rates, new socket rates. I can do that across the, kind of the entire service diagram here. But you can see more than just Kubernetes. So since we're at the OS layer and we track every connection, we can see everything that goes on. We can see, for example, kubelet. This is talking back to my EKS masters. I can see the ELB endpoints that my service is connecting to. Our agents happen to connect back to the APIs for different regions, so you can actually see those interactions. And in all these cases, if we see an external connection, we'll actually snoop the DNS and we'll label it automatically. So we actually do a very good job at showing you all the stuff your cluster may be talking to externally. In this case, it's connecting back to like intake.flowmill.com. So and I didn't have to do anything. This just worked out of the box, right? This was kind of the out of the box behavior that you get. So this is where I wanted to, as a starting point, I wanted to start doing kind of different, chaos engineering around this. So one of the things we would do is potentially look at, let's create sort of a bad service, and change the behavior of some of these services and see how that pops up in the system. So I've gone ahead. I've actually created a misconfigured service before we got going here. It's just a simple deployment. It doesn't do much. It's got one replica. And for folks familiar with Kubernetes YAML, you'll be able to see that basically there's one container here. It's Alpine, and it starts by creating a big file and then posting that file out to my front end. That's all it does. But this will be useful to give us a sense of like the kinds of things that we can see as they become new. So, what I'm going to do here is just apply this misconfigured service. So now it's off and running. It's kind of doing its misconfigured thing. It's going to spin up. I'll do one more thing while we're at it, right? So maybe we'll, one of the other things that you sometimes want to know in your cluster is who's connecting out to the internet, right? So who's making different kinds of external connections. So maybe we'll simulate one of those. I'm going to exec into one of my front end containers, and I'll just do a wget to Google, just for the sake of seeing something going on. And the file's already there. That's fine, but it's still connected out. So we'll make a couple connections out to Google. So, we're done here. We did two different things. One, we launched a new service, this misconfigured service, and then we just did. We had one of our front end containers kind of reach out to Google, and I think the idea would be, let's see, these are all things that you'd want to know about, but you may not, if you ran your own observability tool and it was instrumentation based, you may not have instrumented your system to identify things like that. New services come and go all the time. These new interactions, people turn on new SaaS services. So you want to be able to, see that these kind of things are happening. And that's precisely the kind of stuff you can see happen in Flowmill. So, I just refreshed my service graph, and I can see here from my front end, there's some new behaviors, right? One, I can see the misconfigured service, which actually reached out to Alpine and pulled down its image. And then I can also see its interaction with the front end service. And I can also see the connection out to Google, right? So in this case, we snooped the DNS to know that it's connecting to Google. We couldn't actually run over there. We were running on on the front end where the front end service runs, but we're able to see this interaction too. So the cool thing about the service maps are these are, as Jonathan mentioned, truly complete service maps. By tracking every connection, you're able to see everything that goes on, even stuff that you didn't really think about or expect to be happening in the environment. So that's one of the first things I wanted to show you about how we can do different kinds of service mapping. I don't know if there's, Mo and Anara, if you guys have questions, feel free to, it sounds like you're not shy to interrupt me, so feel free to do that. I've got a few more things I want to show you too.
Calling me out.
No, I appreciate it. So here, well, I'll jump over and show you the first thing I may do is I'm going to turn off our misconfigured service before it does any actual damage to my system, so I can continue my demo. But I was going to cut over and show you guys a little bit more of the view of the cost, how cost works in the system. So Jonathan mentioned, you mentioned this piece of our application before, and I think it's a really interesting piece because we run on each of the nodes and we're able to see how services are distributed across them, we're able to build analyzed views like this, which will actually show you how services communicate across availability zones and out to the internet. And you can see this, we actually break this down from a dollars perspective, as well as from a traffic perspective, like how much traffic different things are sending. The reason it's really interesting, and some users have been really excited about this, is network egress costs are something, the prices are very clearly defined by AWS, but what gets tricky when you're running a Kubernetes-based system is if you start seeing larger costs than you say had last month, it can be really hard to know which of these services that I launched are actually doing it, right? I got 3 Kubernetes nodes. I see that there's traffic between them, but there is 12 services spread across them. I want to know which service actually generated the most cross availability zone traffic. And that's the kind of thing that a view like this can show you. And we know that because we tracked every socket and we actually had we knew how they were labeled, which was going cross zone. So we can show you a view of how much traffic the front end service is sending, say, cross zone or egress, but then also where it's going to. So I can see a lot of it's going to the load generator service. Next is going to the product catalog. So I'll get this ordered view of how traffic flowed through the system, and specifically which was cross zone, which was egress. You can get really detailed views on this. I'll show you kind of a quick example here. So if you wanted to dive into some of this data, you can go to our dashboards. This is a breakdown view of just cross-zone TCP, which is the only traffic that's going on between these things. But you can actually, I would be able to see if there's egress TCP traffic at this time. We can track UDP traffic if that's going on. So it really gives you a pretty fine-grained view of the system, and it lets you figure out which service is driving up network transfer costs and how that maps across your Kubernetes environment. So with that, I'll cut over. I was going to cut over the next demo if there's no questions on the cost side, and we're going to do a little bit more chaos engineering. This time, what I want to do is inject network problems into the environment. And network problems happen for a whole variety of reasons. You operate a big enough system, run a big enough data center, blips happen, blips happen here and there. And what can be actually pretty tricky is to know how they're affecting your services, which happen to be distributed and again, run across a number of nodes. So what I'm going to do here is I am going to inject some packet loss into one of my services. In this case, I'm going to choose one of my front end pods, and I'm going to run the command first, and then I'll explain to you what it does as 0. So just it takes a few seconds to execute. So of course I screwed up the command. And
I was gonna say, I'm surprised you memorized that whole command there.
No, I have to get it wrong. I have to get it wrong at least once, right? So what this command is doing, I know it may seem a little bit obscure. So this is using a traffic control library in Linux, which that's what TC is, and it's in pretty much all the distributions. Basically, it lets you do different kinds of packet mangling. In this case, what we did was we went after each 0 on one particular container. And again, I could have done this on one of the hosts. I could do that. There's a lot of different ways to apply it, but just to be pretty focused, I went after half the front end service, and I added some network emulation that adds 8% packet loss to that container. So now, everything this front end container is sending out about, Linux will throw away 8% of the packets, and that's going to start cycling through my system and causing wreaking some minor havoc over time. So what I want to show you is, well, how does Flowmill help with this kind of thing? So as Jonathan mentioned, you can see those dashboards, you can see obviously metrics of all these things in real time, but what tends to be more interesting is actually looking at kind of an overview of the system to see where these different problems are emerging. So we created these overview pages, and what they're actually doing is they look across a couple different dimensions, and they look for different kinds of problems. So for example, in this tab, are there HTTP errors, and where connections have greater than 1% 500 rate, or is latency higher than 150 milliseconds, or is there a cross-zone latency that's elevated? or kind of an internet-facing latency that's elevated. The tables are all empty now because these problems aren't happening, which is good. It means my system is happy, at least in this respect.
Are these requirements configurable, or are they default with Flowmill?
Yeah, so right now they all default with Flowmill. So the idea is to have a minimum number of things that you have to, that kind of knobs you have to turn. We've worked with different people around, we work with some of our customers around tuning them, but the idea is they just work automatically and you don't have to adjust them or do work around them. But you can, like if people need different things, we've worked with, it's possible to make changes. So other stuff like network latency. So we're able to see things as network latency higher than 50 milliseconds if you're staying within an availability zone, or is it higher, what happens if you're going cross availability zone, right? That threshold might be higher, or internet facing latency may be higher. I'll come back to network in a second. DNS problems, luckily we don't have any here, but one of the other things Flowmill is doing is matching DNS requests and responses to see if there's DNS timeouts. So are there any, are any services failing because the DNS requests are timing out? So we'd be able to show you what services are affected. Sometimes this happens in EKS clusters if people don't have enough core DNS pods, for example. I've seen that to be a common failure mode. And maybe if we refresh this guy, and then eventually he will start showing my problem, which was my front end service. So network tab, we can actually see different kinds of network failures, and this is where the tabs are full because we started adding our particular attack. So the things you see here, connection failure. So we're actually looking for SYN timeouts where it can't actually establish a TCP connection. Packet loss, which was, again, this was the attack we added. We'll look at that in a second. Throughput increase and decrease. So like, are there big changes up and down in a service? And this was the one we just added. So we'll actually look at what it looks like. So we see the front end service. Again, this doesn't show 8% because it's only affecting a part of the service, and it's averaging over time because it doesn't affect every container. But we're able to see that it has this kind of high drop rate and that it's affecting a number of its peers. The cool thing Flowmill lets you do is then dig in on that data. So, so I'll open this tab and we'll look at just say like the front end to the, the front end just to the product catalog. And in doing so, you can see, so we kind of have our packet loss here and our throughput, but what can be interesting is being able to look at groupings of this data. So the reason we can get, what this means is we know every connection. So as Jonathan mentioned, like we're tracking in Linux sockets. So we actually have this very fine-grained view of how every container behaves across every host. But I'm looking at a very aggregated view of how one service talked to another service. But I can actually peel it apart and say like, well, now I know there's a problem between the services. I might want to actually see the IP addresses for the individual pods and see if there's a problem, and see if one looks different than the other. And I'll call out the two graphs here, the throughput rate and the packet loss. And you can actually see, look, we've got two pods, kind of two front end pods here. They're pretty well load balanced. They're both handling about the same amount of traffic. But only one is showing up here in packet loss, right? The purple one, right, .50, it has all the packet loss. The other one doesn't. So what it helped me do was actually look at, as a service owner now, I can look at this and say, great, like, yes, my service has this issue. It's it's affecting a part of my service. It's these pods. I can tell what host they're running on. I can now, it helps me figure out that it's an infrastructure problem, but even what part of the infrastructure is causing it and where the pods are that are causing problem. I can nuke those pods. I can nuke the nodes they're running on. I can now take some action because I know that the service issue, how it's related to the physical environment, which gives me a plan of action I can form around it. So this is one of the powerful things you can get out of the granularity of the flow data, right? You can actually see every flow. You might want to start looking at flows aggregated, but then you want to drill down and be able to see very specific ones. And you can do this across the entire data set for all the different metrics that the Flowmill gathers in the system.
Yeah, this is awesome. If I didn't know that one of the services were working, I would have probably just looked at my front end code for hours and wondered what's wrong.
Yeah, and that happens, and that absolutely that's one of the things that we've seen a lot of people will use this because they want to answer the question before the front end team spends a day looking at their code to see what's broken. They're like, well, maybe there's something in the infrastructure, and instead of looking that after, you can quickly rule that out or figure out that it is that problem and save the developers a lot of headache looking for some intermittent failure in their in their environment.
So I have a question for you real quick, Mike. I'm looking through your docs right now, and I see that there's advanced functionality for like some of these filters, right? And in particular, there's one about directionality because obviously we're seeing right now source to destination. Could you maybe talk? Are there any other options? Can we see like a reverse flow?
Yeah, you absolutely can. So in this case, we're you can look at just one direction. In this case, we're actually filtering both. So but the idea is that do you want to see the traffic just from the front end to the product catalog or from the product catalog back to the front end? So that so the filters will let you control that and kind of get very specific. So the flows do have the data does have direction, right? It goes in one case from front end to product catalog, and then data back from product catalog to front end. And you have a number of controls to decide which you want to be viewing at any given time. And that's why we would have that kind of advanced control, because in some cases a problem might be more evident looking kind of looking in one direction.
Right.
There's also just to chime in, kind of we've built the system to have relatively powerful slice and dice. So if you want to see how kind of the front end container is talking to every availability zone, just aggregate just availability zones. You don't care about the container on the other side, just how much traffic is flowing to that availability zone. You can change the columns on the table to show you that, right? And usually, and again, this was where kind of manipulating kind of this massive data set of like individual sockets and being able to query it relatively quickly comes in.
Yeah. So you can choose any of these groupings, like we're looking at cluster, namespace, and service, but I may just, I could look at just a subset, for example. And that'll control what my lines mean and what appears in my table.
Very cool.
Let's go. So there's, one more demo I thought I was going to show you, show you quickly. It takes a minute or two to run, but the last piece I wanted to do was Hanara's example of, well, what if something really does go wrong in the front end, kind of in the front end service? How does Flowmill help with that as well? So I'm gonna quickly jump into the code. I'm sure people aren't familiar with this particular app, but I opened the file that is within the Go code that handles the front end service. And for anyone familiar with Go, it'll be obvious. Otherwise, I think it'll hopefully be semi-self-explanatory. Is this function handles all the requests to the home, to basically / for the front end service. So it's this handlers.go within my front end service. And I happen to create this little snippet of code here, which I'm going to uncomment now, which does, again, if anyone, a relatively naive thing of randomly deciding to return a 500. And that's all it does. So every once in a while, you'll just get, you'll kind of get some errors back from the service. And this particular app runs with Scaffold. I don't know if folks have used Scaffold. It takes a few minutes to build, but basically what what I'm deploying now is something that will it'll start returning some 500s sometimes in kind of in the environment. And I wanted to show you how you might be able to see that in Flowmill.
Yeah. In the meantime, I had a question for you from a techie thought who is doing numbers today, asking really great questions. In this case, they want to know what's the retention period like for collected data, and is it available as a configuration?
It is available as configuration. Obviously, storing data. We do this ask storing data cost money. So we typically store about 30 days, store 30 days of data. But this is something we work with, different users around, right? Some people want to store longer periods, and it's totally possible. So you can have effectively arbitrary retentions, but usually 30 days is kind of the sweet spot.
Perfect.
I also saw a question about, not a question, but a comment about DNS and how Kubernetes DNS kind of adds complexity in a failure mode to Kubernetes. I just wanted to chime in on that. Yes, we've seen that a lot. And last year at KubeCon North America, I gave a lightning talk about how kind of a few ways that DNS can fail and bring down your system. We've seen this at users multiple times where kind of an under-provisioned DNS service dramatically reduced performance and created in some cases, errors on a live production deployment. We've seen it at ISPs, right? Like big companies, you can have, you really need to pay attention to how infrastructure is affecting your services. So this is why we found that the Flowmill, this is why we found it really important to tackle the network infrastructure observability as part of Flowmill. So the DNS component of it can show you failures that you don't see when you monitor the DNS pods on Kubernetes. There is this famous race condition between IPv4 and IPv6 packets that muscle the Alpine's C library. The DNS resolver there sends two packets in parallel, the IPv4 and IPv6, and the kernel then decides to only map IP tables for one of them, so that it goes through these IP tables that I described earlier. So kind of the kernel just decides just one of them goes through, either the IPv4 or IPv6, and your DNS resolver would only work with IPv4 and would drop those packets. This is something that you wouldn't see. That you would have huge latency on your HTTP requests, and you wouldn't see it. And kind of Flowmill, through monitoring DNS on the kernel, you can see these types of errors. So it gives you very broad visibility into how DNS is performing. Kind of there's multiple outages. There was a good talk at KubeCon by Datadog. So if somebody wants to see, they have this they have a slide that says it's never DNS, and then the never is struck off, right? Like it's always DNS, right? DNS is such a frequent problem on cloud deployments and specifically on Kubernetes that you have to monitor.
Yeah. And I guess, to close the loop on the demo, I started, so we added that, error rate into the front end app. And one of typically, what the other data Flowmill gathers and we color our connections with is the container versions, and the image tags. In this case, our image tags are the Git SHAs. So they're not as friendly as nice names. That's an artifact of how Scaffold works, which was how the app was built. But these could just as well be any names that you want. But the cool thing, if you look here, what you can see was, I filtered down just to see what's going on with the front end, and you can, you can see at the time I did my deploy, I had no 500s for a while, and then as I deployed, I got with a new version, I started picking up, my 500 error rate. So right, it becomes an easy smoking gun of this was a version deploy, and I didn't have to do any additional instrumentation. I was able to, with the previous screens, I could have seen if it was an infrastructure problem. With a screen like this, I can see, no, this really is a developer problem. This really is one that that we should be looking at from where we popped in more 500s. Into the system, exactly when they popped up, what version they popped up with. So this is the other kind of data Flowmill can show you, and as Jonathan mentioned, so you have the you can get essentially layer 7 data out of this system too.
Very cool.
Yeah. So those are all the demos that I brought to show you guys. I think I'm happy to, certainly happy to answer more questions. I'm semi-amazed with myself that they all worked for the most part. It's cool.
Yeah. I'm glad they all worked, first of all. I know you had like Twitch Magic demos just in case they didn't, but I'm glad we didn't have to worry about any of those. Just a quick question, like any parting thoughts to our audience about Flowmill? Someone brand new to Flowmill, I mean, what would you tell them? Yeah, Mike, we start with you.
Yeah, I would say like the great thing about Flowmill is that it just works out of the box, right? Especially for folks running Kubernetes, EKS clusters, ECS clusters, environments that are typically hard to get good visibility on. And it's just it is a tool that will work out of the box and give you a really good picture of what your system is doing. Right? A lot of folks come to us sometimes and they're like, yeah, we just have a lot of services and it's kind of a mess. Can you help? And that's one of the places this Flowmill really shines. And that's one of the cool things that's been about working on it.
All right. Jonathan?
Yeah, we've been extremely excited working with the AWS community. The AWS user community is awesome, and we've loved every interaction. And this is why, kind of like Mike said, we're working on having very low friction deployment. You should be able to get up and running in a few minutes, couple minutes, right? Like we're our internal slogan is 30 seconds. And so we've built an AWS marketplace integration, where anybody can go in and bring up their deployment in seconds. So it's maybe three clicks and you get to the Flowmill page and install. So I would encourage everybody to just try it out. There is a price to it, but we've been able, working with the marketplace team, we've been able to create a system that prorates per minute. So, or per you're used to per second, but we've gotten per minute proration, which is should be very easy. You spin it up with on your staging cluster, and you'll be able to see. We've had a comment about IPv6. Go try it out. Let us know what you think. We'd love to interact with. We love interaction with our users. Frequently, we have Slack channels with our users if they want to. We just I'd encourage everybody to sign on and interact with the team.
Awesome. So we do have one more question. Are there any key differences deploying that versus deploying on ECS?
Oh, when you deploy an ECS, it's very similar. So instead of a Helm chart, we have an ECS task definition, a service definition, and that's all there is. So you would basically, you download those from the UI and you fire them off. They run the same container that we run in Kubernetes for the agents.
Awesome. All right. So thanks everyone for joining. Come back on Wednesday. I think we have Okta joining us. So 2 p.m. Pacific, right? 2 p.m. Pacific, Hanara? I'm not tripping, right?
Yeah.
All right. 2 p.m. Pacific. And then last but not least, Mike and Jonathan, tradition with Howdy Partners that we sign off with one of three things. Western theme, obviously, following the Howdy. So we have Giddy Up, we have Y'all Come Back Now, and we have Happy Trails. And this is one of the first times that I've been able to list them without forgetting them, so I'm proud of myself. But yeah, we'll start with Mike. Which of those three are you going to choose to sign off with?
Happy Trails, everybody.
Happy Trails. Jonathan, what about you?
Giddy Up.
Giddy Up. Hanara?
Giddy Up, because that's easy. I always mess with the second one.
All right. And obviously I'm from Texas, so I got all of them. Giddy Up, Y'all Come Back Now, and Happy Trails, and we'll see everyone soon. Thanks everyone for joining.